Welcome grade 6 to your e-lecture. We have started chapter number 7, forces and their effect. We have discussed in detail force meter, upthrust force, density, balanced forces. Today we are going to start stretchy materials. So I'm going to read the page. Forces can cause materials to stretch. When the forces are removed, the materials may spring back to their original length. This is called elasticity. For example, a rubber band can be stretched to several times its length, but it will return to its original size when released. Rubber is a very elastic material. Metal wires will also stretch and spring back into shape if the forces are small. However, if the forces are too large, the wire will go beyond its elastic limit and be left permanently stretched. So here they are explaining you the concept of elasticity and elastic limit. On the next page you can see that the concept of elasticity was given by the Robert Hooke, and the elasticity is known as Hooke's law. So what happens is that in the rubber or elastic material, when you stretch them, they can stretch to a certain limit. The limit to which any material can be stretched, it is known as its elastic limit, before it will be left permanently damaged. So when you remove the forces that were stretching the materials, all of the materials, they come back to their original length. It is called elasticity. But what happens is that if you keep on stretching the elastic materials, then they will lose their shape. Next, they are explaining you the springs. The springs are very useful because when the forces are applied, they stretch and spring back into the shape.
When we hear the word elasticity, the first picture that comes to our mind is something like this. But is this really what elastic means? We will find that out in this video. Let's take an example of a helical spring. When a force of compression or tension is applied, the helical spring gets deformed, that is, it changes in shape or size. This force is referred to as the deforming force. And the ability of an object to regain its original shape when the influence of this deforming force is removed is called elasticity. More examples of such objects include sponge balls and rubber bands. When compressed or stretched, they get deformed, but they soon return to their original shapes. This self-reversing deformity the object goes through when forces applied and removed is called elastic deformation. But is there a limit to the elasticity of an object? Do elastic objects remain elastic forever? Not really. For instance, if a great amount of force is applied to a spring, it simply won't be able to stretch further than a certain point. But if the force becomes excessive, the spring will get permanently deformed and may even break if we keep increasing the force. Hence, the spring does not remain elastic forever. The elastic limits depends on the deforming force applied on the object and the properties of the material they are made up of. And it is important for engineers to know the elastic limits of things such as metal beams and concrete. That is, the limit to which they can uphold the load without getting permanently deformed or cracked. Now we come to an extremely important topic. The Hooke's law. Robert Hooke, an English physicist, stated that the empirical law in 1660, which is today known by the name Hooke's law. What does empirical mean? It means the law was derived using observations. It states, for elastic deformation in a string, the deforming force is directly proportional to change in length. Consider a spring of length L, whose one end is fixed from the end. Suppose the stretching force F is applied on the other end. Now let the change in its length be delta L. The law states that the force F is directly proportional to delta L. Now what do we mean in mathematics when one quantity is directly proportional to the other? It means that one thing is some constant times the other.
The next concept we need to look at is extension, which is the increase in length of a spring when it's stretched. For example, if we hang a spring from a solid support, then we can measure how the spring's length changes as we add downwards force to the bottom of the spring. If we then add a mass to the bottom of the spring, the weight of that mass will pull on the spring and so increase its length, which we can then measure as the extension. As we increase the force on the spring, For example, we add more mass. The extension increases proportionally, which we can write as F is proportional to E, because F is the force and E is a symbol for extension. We can show this relationship by plotting a graph of force against extension. As the force increases, so does the extension. And because it's a straight line that passes through the origin, we can tell that force and extension are directly proportional. We call this relationship Hooke's law, and we call this point the elastic limit, and the object won't necessarily go back to its original shape.
What is weight? Over 300 years ago, Sir Isaac Newton came up with the idea that all masses attract other masses. He called this attraction gravity. The Earth has a mass of about 6 million kilograms, so its gravitational pull is large. It is gravity which pulls the object to the ground and when they are dropped, and it is gravity which keeps the planet in their orbit around the sun. As you all know about the gravity, it is the force which pulls the things to the ground. It is called gravity, and this idea was given by Sir Isaac Newton. It is the same force which holds all the planets in their own orbits around the sun. Next is gravity and weight. When we lift a bag of sand from the ground, we have to use force. This is because the Earth's gravity is pulling downwards with the force. We call this force weight, and we can measure it with the Newton meter. Because weight is a force, it is measured in newtons. The mass which is being acted on by the gravity is measured in kilograms. The weight of 1 kg mass depends upon the strength of the gravity where the weight is measured. This might seem confusing, but it is easy to understand if you think about taking 1 kg bag of sugar on a very long journey. On Earth, the strength of the gravitational field is about 10 Newton per kg. This means that it gives a force of 10 Newton on every kilogram. The moon is much less massive than the Earth. The strength of the moon's gravitational field is only 1.6 Newton per kg. So if an astronaut buys a bag of sugar in your city, its mass is 1 kilogram and its weight is 10 Newton. If the astronaut takes the sugar to the moon without opening it on the way, its mass is still 1 kg, but on the moon it only weighs 1.6 Newton. So here we are clearing any confusions about the concept of weight and the mass. Generally, when we weigh something, we are weighing the mass, not the weight, because weight is not measured in kilograms. Mass is measured in kilograms. Mass is the total amount of matter in its body, and the weight is the measure of the gravitational pull on that matter, on that amount of matter. And it is measured by Newton meter. As the weight is a force, so it is measured in newtons. Weight changes because of the gravitational pull is different, but mass remains the same. The mass is constant everywhere. How will you calculate the weight? The weight is calculated by the simple formula, which is mass multiplied by gravity.
Have you ever wondered what keeps us floating off into space? Why am I going down after every jump? Well, this is called gravity, an invisible force that pulls you back to the earth. Sir Isaac Newton, a well-known scientist, discovered gravity about 300 years ago. The story is that Newton saw an apple fall from a tree towards the ground. At first he thought, why didn't the apple go up? Then he realized that there was a force that made it fall on the ground, and he called it gravity. The sun's gravitational pull keeps planets orbiting around it. Even the Earth has a gravitational force on the moon. That is why the moon rotates around the Earth. The bigger the object's mass, the more gravity it will have. And the smaller the mass of the object, the less will be the gravity.
When it says 56 kilograms on your bathroom scales, what are you actually measuring? Well, if you said weight, like most people would, then you're sort of wrong. Kilograms are a measure of mass, but the scales actually measure the force of gravity on your mass. So they do actually measure weight, but this should be in units of force, newtons. This is a 1 kilogram bag of sugar. Grams and kilograms are units of mass. Mass is a measure of how much stuff is in something. This bag contains twice as much stuff. It has a mass of 2 kilograms. It would be wrong to say the bag weighed 1 kilogram or 2 kilograms, as weight is a force caused by gravity. To measure the weight, we need a spring balance or force meter. This is a force meter, or a Newton meter. It shows the weight of something hung from it. Let's add the bag of sugar. It shows the weight is almost 10 newtons. Can you remember the equation that links mass with weight? In everyday life, we use the word weight, when in fact we mean mass. The bag of sugar has a mass of 1 kilogram, but a weight of 9.8 newtons. Now let's take this bag of sugar to the moon. The moon is much less massive than the Earth, and so has a lower gravity. On the moon, g is only 1.6 meters per second per second. See how the weight has dropped compared to when it was on Earth? But notice, we still have the same amount of sugar. There is still 1 kilogram of stuff. The weight has changed, but not the mass. Remember that mass is a measure of the amount of stuff in an object, and gives a measure of how difficult it is to get moving or to stop it. It never changes. For example, my mass on Earth is 56 kilograms. On the moon, I would still have a mass of 56 kilograms, as W equals mg, where W is weight in newtons, and g is acceleration due to gravity. On Earth, g equals 9.8 meters per second per second. So the weight of the 1 kilogram bag of sugar is 1 times 9.8, which equals 9.8 newtons, as the picture shows. In everyday life, we use the word weight, when in fact we mean mass. The bag of sugar has a mass of 1 kilogram. Weight is the force due to gravity, and that depends upon the masses of the two objects that are attracted. On Earth, my weight is mass times gravity, so roughly 56 kilograms times 10, which is 560 newtons.